Right, now we covered tons yesterday, and I sort of just talked at you for a long time, so well done on keeping your way through it. But let's see if we can revise it. What did we cover before we got to this idea of an integral? Where did we start? What was the main problem we started with?
We do things not because they are easy, but because they are hard. We will put a man on the moon by the end of
so we started with JFK.
Do it if we don't.
Mathematically, what we started with was the area under a curve. Okay, because curves are weird, they're hard to deal with. Okay. So we moved from area under a curve, right, to this German guy named Riemann, okay, and his clever idea of breaking an area up. Where's my green one? Shoot. Breaking this area up into an infinite series of infinitesimally thin rectangles, and then adding them up and using limits to actually make it exact and not just an approximation. Okay, so that was the basic idea. Now I think where we left off, I gave you an example, but sort of like what we concluded is that if we were to define, and this is an important thing I want you to get down, if we were to define this area, right, underneath f in this case, but not just any area underneath, we want it between certain bounds, and we call them the upper and lower bounds, right? Lower because you start here and you go up. Okay, so between these two vertical lines, x equals a and x equals b. That's what they really are, right? Okay. Riemann defined that, okay, as this infinite sum thing, right? And sigma was already taken, okay, of f with respect to x. Okay, and then at the very end of the lesson when we were dealing with that example question, I introduced a little bit of extra notation, which is to say, look, what this becomes, this process of integrating, is really finding the primitive function, right? So you take that primitive function, and you evaluate it at those bounds, and you take the difference, okay? So taking the difference would mean this. Okay, does that make sense? So, what you've got here, let me circle this. All of these things are really, the reason why I've put it all across is because they're all equal ways of saying, excuse me, the same thing. Okay? Now, probably the most important out of all of these expressions, excuse me, thank you, sorry, is this one, okay? Now, it's so important, I'm going to give it a name, and I'm going to try and unpack it. Good morning, that's okay. The name for this particular one, even though they're all equivalent, is a definite integral, okay? Hence the heading. And what does that mean? Well, we already introduced the idea of an integral. Why is it called an integral? It's because you're integrating, combining all of these little rectangles, okay? But it's called a definite integral because it's defined on certain boundaries, okay? It's an area in a particular place. It's a specific area, okay? It's an actual thing that I can point to, right? However, earlier on we were looking at primitive functions on their own, right? This whole f prime, capital F thing, right? We looked at the idea of just going through this process of integrating without specific bounds, without an actual area in mind, okay? Just going through the algebraic process, okay? So if you go through that process and you don't have boundaries, you don't define it in a certain place, rather than calling it an undefined integral, we call it an indefinite integral. Right? So if we go through the process and don't put an a and a b, we don't put upper and lower bounds, okay? Okay, this thing is called, go back to my other color, an indefinite integral. Okay, now, since it's not attached to a specific set of bounds, right? This part here kind of short circuits, right? Because you're not evaluating it at two different places and then taking a difference. Because there are no places to evaluate it at, okay? Yeah?
Can you have an indefinite integral that approaches a certain value? Like if you have a graph like 1 over x squared plus 1, and it gets smaller and smaller and smaller.
Absolutely, yeah. Now,
but those are still indefinite, even though they're sort of, you can figure out what it is for everything.
Yes, yes. Now, keeping that idea in your head, right? if I take away these bounds, right, I'm not evaluating it anymore, but I'm still going to go through the process of getting to the primitive function. Okay, so this is what we looked at when we looked at anti-differentiation. So this is going to be capital F, but remember, why was the reason why I could ignore the plus C, that constant that came up, right? It's because it cancelled out, right? This process here, the subtraction, meant the constants here and the constants there, so it cancels out. Now, since I'm not doing a subtraction here, right, I can't just ignore the constant. It has to come back, okay? So, a definite integral is an area, right? In fact, it's actually a number. Like, it's 10 units or 50 units squared, okay, and so on, right? Definite integral is a number. The indefinite integral is a function, right? It's a function. Now, it's not just a function, it's a function with the constant, okay? Now, as I've taught this before, people got really confused when there's two different kinds of integrals, and one's got a constant and one doesn't. Like, what's up with that? We shouldn't be that confused though, because we're used to this idea of two different kinds of integrals from derivatives, aren't we? Think about it this way. It's just that we haven't given it the same kind of language, okay? Write this down as an example. Let's consider a nice simple function like, say, x squared. Okay. Now, if we were to differentiate that, right, what would you get? You'd get f dash, that's how we normally call it, right? And that's 2x. Now, you could call it the derivative. We also call it the gradient function, right? Why do we call it the gradient function? Ah, good. If you sub in a value, right, for instance, let's put in x equals 3, okay? You'll get out a number at the end, right? And this is an actual gradient at a specific place, right? This is the gradient at x equals 3, okay? So, it's the same kind of idea, right? If I wanted to give it the same kind of language that we use to describe integrals, right? I suppose you could call this a definite derivative, because it's the derivative and it's defined at a certain place, namely x equals 3, okay? In the same way, I guess this is kind of like an indefinite derivative, because it's like, well, it'll give you the gradient wherever you want it, okay, but you haven't told me where you want it, okay? In the same way that the indefinite integral would give you the area if you gave it boundaries, okay? Does that make sense? So, we don't use this language because, well, actually I don't know why we don't use it the same consistent across both. If I had to guess, I think it's because different groups of people came up with these two different ideas to solve different problems, right? So, you know, maybe. But if you wanted to carry, because I think this is helpful, if you wanted to carry the gradient function in gradient language over to integrals, right, you would call that just an area, right? I already called it that, right? And I suppose the parallel would be, this is an area function, right? Just like the derivative is a gradient function. Okay, it's the function that will tell you what area is. Okay, now, where am I? Oh yeah, okay, good. Should have already drawn that by now. Yeah, I'll leave this here. Okay, so this idea of an indefinite integral, what it really does is it kind of formalizes or solidifies the idea you can do integration and have it as a separate thing from area, right? Because you can think about it as a process which is just algebra, which is what we did at the end of last term, right? I said, look, you guys know how to go from this to that, like if you differentiate, so just go in reverse, okay? And we didn't introduce the idea of area at all, okay? So therefore, what I want to try and help you see the parallel is that we can use this elongated s and the dx, right, as an operator, just like d on dx, right? So this is what we call the differential operator, okay? It means, well, how do you read it? What does it actually tell you to do? If I put something in front, like f, what does it tell you to do to f? Okay, it tells you to differentiate, find the derivative, but it tells you more than that, doesn't it? Because it tells you something different to say this.
Differentiable function. Oh, it's a function in terms of t.
Now, it actually doesn't tell you what the function is in terms of, but it tells you what to do with it, right? So if I have, and when we looked at that exercise on rates of change, right, you would have seen different kinds of d's down the bottom here, d something else, dA, dt, whatever, okay? So it means differentiate with respect to a particular variable, and you pick it out, okay? And you can differentiate with respect to other variables too, right? So therefore, you know, just like this was a differential operator, this is what we call the integral operator, right? So it means integrate with respect to x, okay? So I'm trying to develop this idea that these are inverse operators of each other, okay? Now let me prove it to you. Where did I put my fingers? Let me prove it to you.
Wait, sorry, did you say they're called differential operators and
integral operators? Yeah. So it's this thing on its own doesn't mean anything, right? It's like do this to something. It's a verb. It needs an object. Okay, does that make sense?
Yeah. Wait,
okay.
What are they called?
Operators. Differential operator because it differentiates, and the integral operator because it integrates. Okay. All right. Now, before I prove this inverse relationship and show you how it works, okay, let me just do a quick hot quiz. Do something like this. What's that equal to? Simple question. Not a trick question. X squared onto plus the constant because it's indefinite, right? Okay. How about this? 3x plus c, no problems, right? Okay, how about this?
X plus c.
So there's a 1 hiding in there, isn't there? Okay, it's not a 0. It's not a 0 because otherwise there would be 0 times dx would actually be 0, right? So the fact that there is a dx sitting there means the 1 is implied. So therefore, if you take the primitive of 1, it is x plus your constant, of course. Okay, now just keep that in your head for a second. Now let me prove this relationship to you by thinking of two different functions, one being the derivative of the other. Okay, so I have f and I have f prime. Okay, now keep in mind, right, that the x in brackets, right, we don't actually need that there. It's just a reminder of the fact that capital F and f are not numbers. What are they?
Functions.
They're functions, right? But often we just leave off the x. For instance, when I write this, okay, and then I write this, you know that y is not just a number. You know that y is actually a function of x, okay? But we leave it off because, you know, we already know that, right? So in the same way, I'm just going to leave off the x for a second, okay? I haven't changed anything, I'm just rewriting it shorter, okay? Now, what that tells you is this, okay, which looks very similar to this kind of thing here, which we're used to, okay? It's just that it's a capital F instead of a y, right? Now, see where this is going. I'm trying to show the relationship between d on dx, this operator, and this one, okay? So I need to go from division to multiplication. So I'm going to take that dx, and I'm going to kick it over here. Is everyone okay so far? I haven't done anything too dramatic, right? Okay, now I'm going to integrate both sides. You can differentiate both sides, you can square both sides, you can do anything you like as long as you do it the same, right? So if I just slap the integral operator on the front, what does this mean? I think you know exactly what it means, right? Because when you integrate just a d whatever, right? You just get back whatever the d was, right? Integrating with respect to x just gives you an x, right? So if I integrate with respect to capital F, what should you expect here?
F plus c.
This is just capital F, right? And just for the sake of clarity, I'm going to slap the x's back on so you can see it's a function, right? Plus my constant. And over here, I'm just going to leave that as it is because this is what I wanted to show. Okay, I wanted to show the relationship between the two. They're opposites to each other.